Yes. So what we discussed in the previous class? Anybody? What is the topic we discussed in the previous class? Which algorithm we
Division.
discussed? Yes, yes, good, good. So we discussed division algorithm. Okay. So up to now, the different algorithms we discussed for multiplication, for addition or subtraction, and last we discussed division algorithms. Okay. Now the last topic in the first part of fourth unit is floating point arithmetic operations. Floating point arithmetic operations. Okay. So here, what we discussed up to now is fixed point one. Okay, what we discussed up to now is fixed point. Okay, so in the multiplication or division or addition, we discussed about the fixed point representation of any number. Now we'll discuss floating point. Okay, how we can represent the floating point in computer registers? In computer registers. So what is the difference between fixed point representation and floating point representation? So what are the advantages of having a floating point number representation? Okay. So the main thing is the floating point number is divided into two parts. It is divided into two parts. One is mantissa and another one is exponent. Mantissa and exponent. Okay. So floating point number can be represented as, okay, floating point number can be represented as m into r power e. Okay, m into r power e, where m is the mantissa. Okay, so m is mantissa here. M is mantissa and e is exponent. E is exponent. Then what R? R is radix. Okay, R is radix here. Okay, so what is radix? What is mantissa and what is exponent? Okay, see, for a decimal number, for decimal number, what is the radix? Radix is equal to 10. Okay, radix is equal to 10. So we can call it as a radix or base. Both are same. Okay, we can, what is the decimal for a base is equal to 10, or we can call a base as radix. Okay, base as radix. So for decimal, the radix is 10. Okay, for binary, anybody? For binary, what is the radix? Yes?
2.
Yes, good. So for binary, radix is 2. Okay, binary radix is 2. Now, for example, if I take like 425.25, okay, so this is the number 425.25 can be represented in the floating point representation as m is equal to 42525 and e is equal to 3. Okay, so I can write like this. I can write like this. Okay, point 42525 into 10 power 3. Okay. See, this 425.25 can be represented like this. Yes or no? See, 0.42525 into 10 power 3. How much it is? It is equal to 425.25. Okay, so this part is called mantissa. Okay, this part is called mantissa, and this is called exponent. This is called exponent, and 10 is called radix. 10 is called radix. Okay, so the number 425.25 can be represented in the floating point representation as m is equal to 425.25 and e is equal to 3. Okay, e is equal to 3. Okay, so so here the floating point number, the floating point representation increases the range of numbers that can be accommodated in a given register. That means if you use the floating point representation, a large number we can represent. Okay, the range of the numbers will be large compared to fixed point representation. Okay, compared to fixed point representation, so we can represent the large range of numbers. Okay, so for example here, suppose we are having 48-bit computer is using the 48-bit words. Okay, 48-bit words that computer is uses. Okay, and in this 48-bit, one bit is used for the sign. Okay, one bit is used for the sign, and 47 bits are used for the magnitude. Okay, 47 bits are used for the magnitude. Okay, for magnitude. So here, using the fixed point representation, using fixed point representation, okay, the range of numbers, okay, the range representation, the range of numbers, the range of numbers will be, the range of numbers will be plus or minus 2 power 47 minus 1. Okay, why it is a minus 1? Why it is only 47 means? Why it is only 47 means the magnitude bits are 47 bits. Okay, the magnitude bits are 47 bits. Why minus 1 is here? Because 0 is also we are considering. Okay, 0 is also we are considering here. So the total number, the range of the numbers, if you use the fixed point representation will be plus or minus 2 power 47 minus 1. Okay, so it is approximately 10 power 14. Okay, so 10 power 14. The range is here 10 power 14 numbers, 10 power 14 numbers we can represent. Okay, but this is for fixed point representation. And if you use floating point representation, if you use floating point representation, uh, and here total we are having 48 bit, so 36 bits are used for, okay, 36 bits are used for mantissa, 36 bits are used for mantissa, and 12 bits are used for exponent. Okay, so 36 bits are used for mantissa and 12 bits are used for exponent. So the range of numbers will be, okay, so the range of numbers will be plus or minus 1 minus 2 power minus 35 into 2 power 2047. 2047. Okay, so it is approximately equal to 10 power 615. Okay, 10 power 615. చూడండి, fixed point representation, the numbers we can represent is 10 power 14, and here in the floating point representation, the numbers we can represent as 10 power 615. Okay, so large numbers we can represent in a floating point representation because the power is here, that is 2047. See how 2047 occurs means here this is 2 power 11 minus 1. Okay, 2 power 11 minus 1 is 2047. Okay, so that is the advantage having floating point representation. Okay, generally in the computer, generally we will use the floating point representation. Floating point representation we will use. Okay, for example here. Okay, so for example, if we are having 8-bit processor, okay, suppose we are having 8 bits processor, okay, or a microcomputer we are having, okay, 8-bit microcomputer we are having. Okay, so in this 8-bit microcomputer here, suppose if you take this one here, so 36 bits are 36 bits are used for the mantissa means, okay, 36 bits are used for the mantissa means we can take how many, that 5, what is 5 registers we can take, 5 registers we can take. Okay, or if you take 4 words, if you are using the 4 words here, okay, 4 words are used to represent floating point. Okay, 4 words are used to represent the floating point in a 8-bit microcomputer. 8-bit microcomputer. So here 24 bits are used for the mantissa. 24 bits are used for the mantissa, and what is 8 bits are used for the what is exponent. That indicates out of 4 words, 3 words are used for the mantissa, and 1 word is used for exponent. Okay, 1 word is used for exponent. Suppose if you want to represent in a 8-bit microcomputer, 4 bits, if we are using the 4 words for floating point representation, out of 4 words, the mantissa we can represent in 3 words, and 1 word can be represented in the 1 word we can accommodate the exponent. Okay, 1 word we can accommodate the exponent. Okay, here, so arithmetic operations with floating point numbers compared to fixed point numbers. Okay, so one advantage of using the floating point number is the large numbers, the range of numbers will be large. Okay, Then if you compare with the fixed point, some what is limitations are also we have to do. We have to take the consideration of limitations. So first one is it is more complicated compared to fixed point numbers. The representation of floating point numbers are more complicated and execution takes longer. Okay, execution takes longer. That means if you want to execute any program, it will take more time. If you compare with the same program with the fixed point numbers, fixed point number representation, and it required more complex hardware. Okay, it requires more complex hardware. Okay, so these are the limitations. Okay, disadvantages. These are the limitations of floating point numbers. These are the limitations of floating point representation when compared with fixed point numbers. One is it is more complicated and execution takes longer and required more complex hardware. Okay, so any doubt up to now? Please ask the doubt. Only 24 members came. Vaishnavi, is it okay? Vaishnavi.
Okay, sir.
Okay. Vishnuvardhan, N. Vishnuvardhan. N. Vishnuvardhan. Sai Teja. Sai Teja. Manasa. Is it okay, ma?
Yes,
Is
sir.
it okay? Yes.
Yes, sir.
Okay. Yes. Fine.
So,
Chappandama.
so what is a mantissa?
Yes. What's your doubt?
So, what is mantissa?
Yes. Yes. See here, so mantissa. Okay. See, in the floating point representation, this is the word we are using, the mantissa. Okay, mantissa may be here integer or fraction. Okay, so that part we are considering it as a mantissa. Okay, so this is mantissa and this is a radix and this is an exponent. But what is mantissa means? It is a number. Okay, it is a number, but that number may be a integer, it is in integer format or it is in fraction. Okay, it is an integer format or it is a fraction. Okay, generally we will use as a fraction here. Just now I have taken the example here. So 525.25 into 10 power 3. Okay, 10 power 3. Sorry, 1 minute. So this number I have taken, I think, yes, 425. Okay, 425. So fraction I have taken 0.42525 into 10 power 3. Okay, so this is nothing but the mantissa. Okay, so this is a fraction. This is a fraction here. Okay, so this number 42525 is a mantissa and 3 is nothing but exponent. 3 is nothing but exponent. Okay, and R. This is the R. What is base? And here we are not storing anywhere the radix. Just we are assuming that the radix may be 2. Okay, radix is 2 in the digital computer. The radix is 2. So that is why we are not storing the number 2 in any register. Just we will store this mantissa, and this exponent is stored in registers. Okay, because by default in a digital computer, by default the radix or base is 2. Okay, the radix or base is 2. Okay, so antanama arthamenda, just it is a number, that's it. Selina, have you
Okay,
understood?
sir.
Just it is a number, just it is a number only. Okay, just it is a number. Okay,
Yes, sir.
now here, yes, anybody? Is any doubt? Okay, so here adding or subtracting two numbers, requires some alignment of the radix point, since the exponent parts must be equal before adding or subtracting the mantissa. Okay, so the what is if you are performing addition or subtraction, we have to do that operation between the mantissas of two numbers, between the mantissas of two floating point numbers. And before doing this one, you have to do some alignment, where you have to do alignment in the exponent part. In the exponent part, you have to do some alignment. Okay, for example, if I take, suppose if I take 0.5372400 into 10 power 2, and another number I am taking 0.158 into 10 power minus 1. Okay, now I have to add these two numbers. Okay, now I have to perform addition between these two numbers. Okay, now I have to do some alignment because the exponent are not equal. See, the first number, the exponent is 2, and in the second number, exponent is minus 1. To perform addition or subtraction, the exponent must be equal. Okay, so exponent must be equal. Exponent must be equal. Okay, then you have to make some alignment. Here. Okay, so there are two ways are there here. There are two ways. So this exponent is, we have to make it is a minus 1 by changing the mantissa. Okay, that means by changing the exponent of first number, by making equal the exponent of first number to the exponent of second number by shifting the mantissa, or by changing the exponent of second number, it should be equal to the what is exponent of first number by shifting this number, that means by shifting the second number mantissa. Okay, see actually how much it is generally, if you discuss, that is in the integer part. So how much it is? It is a 53.724. Okay, then how much it is? 0.0158. Okay, so now I am taking the first number. And I am writing, and what I am doing means here, I am making equal to the second exponent. Okay, just here what I am doing means here 5 37.2400 into 10 power minus 1. 10 power minus 1. Okay. So how much it becomes? It is 53.724. Okay. So I can represent 53.724 like this one or like this one. Okay. Like this one here. Ante kadandi. Sorry. Yes. Now here, if I am shifting these mantissa, if I am shifting these mantissa left side, okay, if I am shifting the mantissa left side by 3 points, okay, so this is the mantissa I have to store in any register. I lost 537. I lost most significant bits I lost. Actually, the mantissa is 5372400. But after doing this one, after alignment, my number becomes 2400, which is a large change occurs. Okay. See, what you are doing, you are adding or subtracting two floating point numbers. But one condition is that if you are adding or subtracting, exponent must be equal. That is a condition here. That is a condition. Okay. So one of the way to make the exponent equal is by aligning this one, by aligning the exponent of first number, by aligning the exponent of first number by shifting this one mantissa, by shifting this mantissa. Okay, so if I do this one here, the most significant digits will be lost here. Okay, so I can add what is 0.2400. I will make it 000 here and 10 power minus 1. So I can add second number with the first number. But what is the problem? The most significant digit I lost. Okay, and second thing is I can make the exponent of second number equal to the exponent of first number. Okay, so what I can change like this: 0.000158 into 10 power 2. Okay, 10 power 2. Okay, so if I do this one, I will get the same number here. Chudandi, 0.10 power 2, 0.0158, which is the same number, original number. Okay, so if I do the exponent of second number alignment here, okay, so what is the mantissa I got? 000158. This is the mantissa. Okay, so this is the mantissa I got, but I lost the LSBs. Okay, for example, here I have taken 4 zeros. If I take 1256, so I lost the least significant bits I lost. Okay, least significant bits I lost. Okay, so losing most significant bits are better, losing least significant bits are better. Which one is better? Which one is better? For accuracy point of view. For accuracy point of view, losing most significant digits are better or least significant digits are better. Suppose మీకు అర్థం కాగలంటే suppose if I take the number 2357. Okay, 2357. Okay, now if I remove MSB, what is the number? 357. Okay, if I lose the least significant digit, what is my number? 235.
230.
235 here. Okay, 235, and I will make it as a 0, or I will make it as a 0. Okay, so which is better? Which is better?
357.
Which is better? For accuracy point of
Second
view,
one.
yes.
Second one.
Second one is better kada. Okay, having the 4-bit register on my. So this is the 4-bit register. My number is 2357 on the. Okay, so I deleted this one. So 357 by shifting left side. By shifting left side, so 3570. Okay, or if I delete the least significant digit, if I delete the least significant digit, and if I shift the right side, it becomes sorry, it becomes what it is, 235. Okay, by making a 0 here. Okay, so which one is better as an accuracy point of view? So 2350 is better because the difference is only 7. The difference is only 7 here, but here the difference is 1000. The accuracy point of view, deleting least significant bit is the better option compared to most significant bit, because it is having the weightage is more. The weightage is more. For example, if you take 2357, okay, so the weightage of this one is 10 power 0. Okay, but the weightage is 1, 2, 3, 10 power 3. Okay, so deleting the least significant digit is the better option for going for approximation. Okay, so the second thing is best one. The second option, while we are adding or subtracting two any two floating point numbers, if any two floating point numbers, the second option is the best one. Okay, that means take the exponent which is less. Okay, take the what is exponent which is less and align it. Align it. That means alignment of less exponent value is the only one option. Only one option for accuracy point of view. Okay, so you got this point, yes or no? Yes. Okay. So here actually here it is 158 together basically. Then how many times I have to shift right side? How many times I have to shift right side means the difference of this exponent and this exponent. The difference, that means 2 minus of minus 1, that means 3. Okay, so 3 times you have to shift right side. Okay, 3 times you have to shift right side. So I am getting, so 0.000158 into 10 power 12. Then I got the first number and second number which is having the same exponent. Now I will add or I will subtract. Okay, I will add or I will subtract because the two exponents are equal. Okay, two exponents are equal. Now I will go for addition or subtraction. Okay. Okay. So after normalization of mantissa or by shifting the mantissa, sometimes overflow will occur. Okay, sometimes overflow will occur. So how to make it? How to make it means, for example, after adding, okay, after adding or subtracting, okay, after adding or subtracting, if overflow overflow occurs, if overflow occurs, that means you are adding 4 bits and 4 bits. If you are adding 4 bits plus 4 bits, If the result is a 5 bits, then that indicates the overflow occurs. Then what you will do is here. For example, 4 bit ఉంది కదా మీకు. Suppose మీకు what it is 1 2 5 6 వచ్చింది అనుకోండి. Okay, so another number 2 5 6 7 వచ్చింది అనుకోండి. Okay, so the result is okay, something like here 9 చేస్తున్నాం ఒక నిమిషం. 9 చేస్తున్నాం. Okay, what you will get here? Enter 13 7 5 12 8 11. So you got a 5 bit as a result. Okay, then 1 1 8 2 3. Okay, 1 1 8 2 3. Okay, then what you will do is here just shift the result, which is 4 bit 1, what is 1823 here. Actually it is 11823, but it is a 4 bit result, so 1823, you got a 1823. Okay, so at this time what you will do means shift right side by 1. Okay, that means 1182. Okay, and make exponent should be increased by 1. Okay, exponent should be increased by 1, so that we will get the correct answer. Here. Okay, so if overflow occurs, so how to overcome this one is shift the sum once right. Okay, shift the sum right side by 1 position and incrementing the exponent by 1. Increment the exponent by 1. The problem of overflow will be minimized. Okay, for example, if underflow occurs, what will happen? Okay, if underflow occurs, for example, if you are doing 5 6 7 8 0 into 10 power 5 and what is 0.56 430 into 10 power 5, and you are subtracting this one. Okay, how much you will get? 10 power 5. Okay, 0 ఎంత వస్తుందండి? 5 and 3 0.00. Okay, so 00 will be the MSBs. 00 will be the MSBs of a result. If this occurs, we can call we got a underflow. Occurs. Okay, underflow occurs. So what you will do here is shift the result left side by 2 times. Okay, that means 35000. Okay, and what is decrement the exponent? Okay, decrement the exponent, so 10 power 3. Okay, decrement the exponent 10 power 3. Okay, so when underflow occurs, you have to do this one. When overflow occurs, you have to do the what I discussed in the previous slide. Okay, so whatever it is, it is the number is 350. Whatever it is the number 350 only. Whether you are shifting the left side or right side, the number is the same. Here. Okay. So this is the what is when underflow or overflow occurs, what you have to do. Okay. But in the floating point representation, the alignment is not necessary. Alignment is not necessary. What is for multiplication and division. Okay, for multiplication and division, what is alignment is not necessary and that is not required. Okay, not required. So alignment is not required for multiplication and division, and that alignment we are performing in addition and subtracting, addition and subtracting. Okay, so when you are doing multiplication, okay, suppose you are doing the multiplication here, okay, so you are doing the multiplication, just multiply, okay, just multiply mantissa, okay, multiply mantissa, okay, multiply mantissa and add the component, and next one is add the exponents, okay. So for multiplication operation, so multiply the mantissa, multiply the mantissa. Suppose here it is having the number one. Now what is the first number mantissa and the exponent? Okay, so this is the mantissa and this is the exponent. Okay, for second number, you will have the mantissa and this is the exponent. Then what you will do means here, just multiply the mantissa here. Multiply the mantissas of first number and second number and add the exponents of first number and second number. You will get the multiplication. Okay, you will get the multiplication. For division, okay, for division, okay, so divide the mantissas, okay, divide the mantissa and subtract the exponents, subtract the exponents. Okay, so this is a mantissa 1 and this is mantissa 2 and this is the exponent 1 and this is the exponent 2, this is the exponent 2. Then for the division operation of two numbers, division operation of if you are performing what is the division operation between two floating point numbers, then what you have to do means here, divide m1 by m2, divide m1 by n2 and subtract the exponent, that means e1 minus e2. Okay, so here you have to do e1 minus e2, then divide what is m1 by m2. For in this case, you have to multiply two mantissas m1 and m2, and here in the exponent just add e plus e. Okay, this is for one. This is okay. So the problem of alignment is there in addition or subtraction. Then in the multiplication or division, there is no need of alignment. There is no need of alignment. Okay. There is no need of alignment here. Okay. Now, here in this case, what we are doing means here, the mantissa can be represented in a fraction, and exponent can be represented as a biased. Okay, biased. Actually, the mantissa can be represented as a fraction or integers Exponent can be represented biased or what is signed magnitude form, or what is or signed ones complement form, signed ones complement form, or signed two's complement form. Okay, two's complement form. Okay, so exponent can be expressed as biased, signed magnitude, or sign one's complement, sign two's complement. And mantissa can be represented as a fraction or integers. But what we are assuming this one is a mantissa is represented as a fraction and exponent is expressed as a biased here. Okay, biased here. You know, sign magnitude representation, signed complement representation. What is biased representation? What is a biased representation? For example, exponent, the range of exponent is minus 50 to 49 అనుకోండి. Okay, why 49 means including 0. Including 0, it is a 49. Okay, the exponent can be represented in the negative numbers or positive numbers. The range is minus 50 to 49. Take an example. Okay, then in the biased form, if you add plus 50, what you will get? The exponent range. What you will get? Exponent range is 0 to 99, kada? 0 to 99. Okay. 0 to 99. That means whatever the exponent in the previously, okay, bias it. That means add it. Okay, add some number to it so that you will get all the numbers are positive numbers. All the numbers are positive numbers. But in the previous case, combination of negative numbers and positive numbers. Okay, if you use sign magnitude representation or what is sign complement representation, the numbers are negative numbers and positive numbers. Okay, but if you use the bias representation, the exponent values are all positive numbers. All are positive numbers. Okay, so it is very easy to represent the positive number because we are assuming that the exponent values are all positive numbers. So there is no need of using the sign bit. There is no need of using the sign bit. Okay, are you getting my point? What I'm telling now? Yes or no? Yes. Yes. Divya, Pujita, Amma Pujita, are you getting?
Yes, sir.
Yes. Okay. Then here actually here the numbers. Okay, here. Okay. Then this 0 to 99, 0 to 99. The positive numbers are, okay, the positive numbers are 50 to 99 kada, and the negative numbers are 0 to 49. Okay, 0 to 49. Of course, this is the original values. Negative number or positive numbers are this is the original minus 50 to 49. But after biasing, all are become 0 to 99. The numbers are become 0 to 99 by adding 50, by biasing 50. Okay. So in this, the range 0 to 99, the numbers 50 to 99 are positive numbers and 0 to 49 are negative numbers. Okay, then how to take back the signs? How to take back the signs means just subtract minus 50. Okay, after doing the operation, if you subtract 50 from the resultant exponent, you will get the negative number or positive number. You will get the negative number or positive number here. అంతే కదండి. See here, minus 52, 49 అంటే నెగిటివ్ నంబర్స్ రేంజ్ ఏంటండి? మైనస్ ఎంత వస్తుంది? minus 52. How much you will get?
-1.
Yes. And positive number 0 to 49. 0 to 49 here. Okay. Then how will get back here? How we will get back? Just subtract minus 50. So you will take the result as a negative number or positive number. Okay. So this is how we are using the floating point representation in the digital computer. Okay. So we are having the register configurations. Yes, Chapanama.
Sir, but 0 is not positive, no, sir.
See, 0 is, we can by default we are, see, minus 0 undanukondi plus 0 undanukondi. Okay, you will take it as a positive number only. Yes. Yes, by default you are taking 0 as a positive, not a negative number. Okay.
Okay, sir.
Now, yes. So in the how you are taking the registers in this one? Time and 2:57. Okay. Now, within 2 minutes, I will complete here. Okay. Now, please see here. So the register B, register A, register Q we are using here. So the capital letter indicates these are storing the mantissa. Okay, the capital letters B, A, Q. These registers are used to store the mantissa. And the smaller letters are used. It is used for exponent. So the total register is B register. Okay, the total register is B register here, or we can call it as a BR register. Total, it will have the floating point number. In this, again, it is divided into 2. Okay, so it is storing the mantissa and it is storing the exponent. Of course, the MSB in the mantissa is storing it as a sign bit. Okay, sign bit. Similarly for A and Q. So these are storing the mantissas here. These are storing the mantissas and these are storing the what is exponent. These are storing the exponent. Okay. Now this parallel adder will be there. For addition of the two numbers. Okay, addition of two numbers. Suppose if you take B plus Q. Okay, so these are the inputs for the parallel adder, and the result is stored in the accumulator. If any carry generated, that is stored in the E flip-flop. If any carry generated during the addition, it is stored in the accumulator. Okay, and here there is no comparator is required here. There is no comparator required while adding the mantissa. But for adding the what is exponent, comparator is required. Because you have to do some alignment. అంతే కదండి. ప్రీవియస్లీ మనకి ఎక్స్పోనెంట్ ఏమొచ్చిందండి? మనకి 10⁻⁻2 వచ్చింది, తర్వాత 10⁻1 వచ్చింది. We have taken. Okay, so -2, 1 are compared. -1 and 1 are compared here in the comparator. Okay, so which will have 3 outputs. Okay, equal, equal or greater or less, greater or less. So the comparator is having the three outputs, whether two exponents are equal, or first exponent is greater than second exponent, or first exponent is less than second exponent. By seeing the result, we will go for alignment of this one. What is exponent? By alignment of the exponent. But here comparator circuit is not there in the mantissa part, because you are not comparing the mantissa. Okay, you are comparing the exponent only, because you have to do alignment for exponent. Okay, so this is the register how we can use for floating point operations. For floating point operations. Okay, so any doubt here? And here, one observation, if you here in the mantissa registers, you will have sign bit. You reserve one bit for the sign in the mantissa, but you are not reserving the, one bit for the sign, because all are positive numbers. Exponents all are positive numbers, because you are biasing other. Okay, because you are biasing the exponent, that's why the exponent all are positive numbers. So the what is sign bit is not necessary. Sign bit is not necessary in the exponent part, but mantissa is having the sign bit, is having the sign bit. That is the observation you have to do. Okay. So sorry, all the time is over. Time 3:32. Okay. So please leave the class. If you are having a doubt, you can ask in the next class. Please leave the class, Ma. Please leave the class. If you are having